Okay, here's convex mirror. Convex mirror actually diverges the light rays. Instead of focusing them, it spreads them out. And as you see here, the light rays that came in parallel will appear to have come from the focal point, and that focal point actually is virtual. You can't really touch it with your finger because it's in the virtual world versus here's where you are. So you cannot go behind the mirror. You're not Alice. Anyway, so the idea is the same. Anything that came in parallel will bounce back through focal. If it was intended for the focal point, then it will bounce back parallel. So here's how you do it. Your images for this type of mirror are always virtual, always upright, and always smaller. That's why on your passenger side mirror, they have to write that objects are actually closer than they appear, because you see them smaller, and your brain automatically thinks, okay, it's smaller than real, which means that it's far, far away. That's why it appears smaller, but they actually are closer than they appear. It's just the purpose of that mirror is to give you a bigger view of the road so you can see it. All right, so again, parallel, focal, focal, parallel. So here's the first one, came in parallel to the main axis, which is this sucker. So it comes in, and it will bounce off of the mirror as if it had come from the focal point, because if you extend it, here's where it comes. If it is aiming for the focal point, it will bounce back parallel. As you see, these two light rays won't cross in real world, but they're not parallel either. So your brain extends them, and they do appear to cross behind the mirror. So that's where your image will be formed. Upright, dead giveaway that it's virtual, it's not real, because real images are always flipped. So upright image, and it's smaller no matter how far away from the mirror you are. So not diverging. This is a convex mirror. For a convex mirror, it's always the same. No matter how far the object is, it's always going to be smaller, always going to be virtual as far as image goes. So here's one thing about this mirror that you need to remember is that the focal length is negative because, again, it's virtual. You cannot touch that point right there with your finger. You cannot measure. Like if this was a convex mirror, then you could touch the focal point, you could measure the radius, and you could figure out the positive normal focal length, which is a positive one. Here, focal length is negative, which is very important because you're going to have that minus screw you over if you do not remember it. So here's basically the same problem. The only thing that I changed is that it's a convex mirror, and in that case, I don't even have to tell you that your object is upright and it's smaller, and magnification is sort of the same but not really. So let's figure out, again, magnification is negative di over do or high over ho. In your case, it's upright because it's a convex mirror, so therefore high over ho is 15 over 45, which is 1 over 3, not negative. But di over do is still with a minus, so negative di over do equals 1 over 3. From there, your di is going to be negative do over 3. So therefore, now I'm going to take the same formula, 1 over f equals 1 over di plus 1 over do equals 1 over do, right there. And then instead of di, I'm plugging in negative. I flip it because I'm dividing by di, so it's negative 3 over do, which gives you negative 2 over do. Focal point is half of the radius. Focal length is half of the radius, but you need to remember that since it's a convex mirror, it's going to be negative. So it's not negative. It's not 10, it's negative 10 in this case. So 1 over negative 10 equals negative 2 over do. From there, do is 20 centimeters.